you how to light your burners and doing the pennies. So hopefully you'll understand why I've been bouncing around. Is everybody amazed at your gold penny when you get home? Pretty cool. Maybe the leprechauns will find it tomorrow. Okay. So those of you at home, my apologies. I had a 2-hour meeting after school yesterday, so actually went over a little 2 hours anyway. I did not get the movie made. I got it made during my prep, but I didn't get it uploaded to YouTube. I will do that right after school. So, you know, and that way. Yes. Yes. Help yourself. Okay, so what are we doing today? We are going to see if you have questions, like I said, on the Alchemist Streamlab. And then we will be doing some notes. So who's pajamaed up? Who's got spirit? Yes, you do. Those are pajamas? Oh, it's just dressed down. Okay, okay, it's good. You're good. Oh, you got a bathrobe on, for crying out loud. Okay, I can see that. So Jack and Gwen and Haley. Who else? Taylor and Gabby. Anybody else? Michael. Sweats. Okay, Bethany. Okay, Caius. Your Christmas PJs. Someone had on sloth PJs earlier. So. All right, so I will get you your hero pointage. Those of you at home, I'm sorry, you're probably in your PJs anyway, so that's just not fair. Just kidding. All right, so what we're going to do, Gabby, is see if you have any questions on this. A lot of you were doing the questions as you went along yesterday. Does anybody need any assistance with anything on the lab? Yeah, you just have to finish up the questions. You get your observations hopefully already. You've made your penny and impressed your friends. Make sure you do these before Thursday, okay? But don't do them now. Pay attention to what I'm doing now, all right? Nobody has questions about the lab? Beautiful. Yes, sir. Yes. I'm going to post a video of. Oh, good. Watch my video that I post after school. Sorry about that. I didn't get it done yet. All right. And then I just remembered that I didn't post these, but that's a good thing because there's 2 typos. So in case you didn't know how to do this, when I transferred my document from Google Docs to, from Microsoft to Google Docs, it changed the Greek letter into the American alphabet letter that it's supposed to be. So sigma is a Greek letter for S. And we're going to, I need to change that really fast. First period got to do it on their own because I didn't realize it. So just so you know, you can type to insert menu and go down to special characters. You probably used some of these for math previously. I know we did before. And you go symbol. And then you type in the word, the name, sigma. You should be able to pull up. You won't need to because I'm going to have it posted yet. Also, people were having trouble with this first period. I don't know why it wasn't working, but you can draw it with your trackpad. Have you guys done that before? So you can also draw it, and it supposedly will pull up the right choices. And I pulled up one. Oops, I got a little goober on there. That's why I didn't like it. But it should just go whoop. Keeps going up like that. So anyway, I'm terrible at drawing on it, but I should already have a sigma in the parentheses for you. And then, of course, the other Greek letter, which you already know because it was Sunday. Anybody celebrate Pi Day on Sunday? Albert Einstein's birthday, March 14th. He should have. But pi, everybody knows pi from math already, so it's not a big deal. And so as soon as you hit return and put that in, it usually pulls it up for you, and it did. Okay, so now they're all set, and I'm going to give you these documents. I wasn't sure what we're going to use them yesterday or not. These are note sheets. They're ungraded. They're not due. You don't need to submit them. So you should be getting those right now. Yeah, you can take notes on your own, or you can take notes on this. You did not assign them yet. Okay, one more try. I don't know how, because it says, why does it say there's an error? Oh, heavens to Murgatroyd. Do you have sigma and pi in the parentheses? Did anybody else get them? Okay, let me try it one more time. I don't know what Google is doing. They're failing me. Nothing but time. We got nothing but time. Nothing better to do, Google. Woo! Oh, it says it went. You guys have it now? Yeah, but I got 2 error messages, you understand. So that's why I was double checking. All right, it says it went. So hopefully it shows up for you sooner rather than later. And most of the pictures from the PowerPoint are on there. And let's get rocking and rolling. So static electricity, you guys are all familiar with it. I'm sure it is when there's a buildup of charge on one or the other surface, and you can use that, surprisingly enough, for spray painting. Who knew? So I don't know if this is a cool car still in 2021, but in 2007, when this book was published, I guess that was a cool car. And of course, red cars are always cool. So yeah, you got to have a hot rod, right? So they're just showing you the application, or one of the applications kind of related to this. So we've talked about different kinds of bonding. In chapter 7, we talked about ionic bonding. Chapter 8 is all about covalent bonding, or making molecules. And we're going to talk about molecular orbitals now. So again, you should remember from chapter 5 a while ago that s orbitals, p orbitals, d orbitals, f orbitals, all that stuff we were talking about way back when on electron configurations, they have different shapes. So s orbitals are spherical, p orbitals are the dumbbell or the peanut shape. Styrofoam tinker toy, literally tinker toy models, for you to view of the p orbitals. These are what we call atomic orbitals, and so they live within the atom. They help us figure out where the electrons live within an atom. But atoms, bless you, don't normally hang out by themselves. Only technically, really, the noble gases do. The metals have that metallic bond thing where they're the cations swimming in a sea of electrons. These atomic orbitals have to merge in order to make molecules, right? So let's just review one other thing. Ionic bond, covalent bond. Turn to your neighbor. What's the difference? Talk about it with your neighbor. What's the difference between an ionic bond and a covalent bond? All right. Lauren, what's an ionic bond? Between ions. Good. And John, fart whistle. What is an ion? Nope, that's isotope. What's an ion, Galileo? It is an atom. What about it, though? It could be a group of atoms. Yes. So in an ionic bond, we've got a cation and an anion. Which one lost the electron? Go ahead, shout it out. Cation, right? Because it becomes positive. So lost electron, or 2, or 3. The anion, that's a prefix that means negative, gained an electron because electrons are negative, the atom becomes more negative, right? So you end up with a positive piece and a negative piece, and they stick together because they're opposite charges. Covalent, like co-workers. What do? Oh, I missed. They do work together. With what? We're talking atoms now. Valence electrons. They share. They work together and share valence electrons. Okay, so one electron usually comes from one atom, one from another, and then they share them because orbitals are supposed to have 2 electrons in them. Molecular orbitals are when atomic orbitals overlap. And remember, think about the orbitals as clouds. There are regions in space where 90% of the time you're going to find an electron, not a guarantee. And just like clouds can kind of merge onto each other in the sky, the clouds of the regions where electrons live in atoms can merge as well. Remember, valence electrons are on the outside of the atom. They're going to be the first ones to bump into the outside of other atoms, and they can make molecules. So simplest atom, hydrogen, 1 proton, 1 electron. Hydrogen is in group 1, and it is on the line 1, and it's in the S block. You guys remember that? And then these last 6 columns are the P block. The middle transition metals are the bases with the donuts, the D block, and then the freaky flowers down here, F. S, P, D, F. You guys remember that? Like a bad dream? Okay, so 2 and 6 makes 8. Not a trick question, which is your valence electrons, and 8 electrons makes a octet. So if you're a noble gas, you've got your 8 valence electrons. Okay, hydrogen doesn't. It has 1 stinking electron with 1 stinking proton. Those electrons want to buddy up with somebody, and so this is the reason that hydrogen is a diatomic element. Those hydrogen atoms coexist in space. They get close to each other. Their clouds kind of end up the place. That just means where the electron is going to often be in between the 2 nuclei, okay? And if they get close enough, the energy actually drops, and they actually coexist very nicely as a diatomic element. Molecular orbitals are unique to a molecule, just like atomic orbitals are unique to atoms. Because molecules have to have bonds, they also are called bonding orbitals. All right, let's get into the sigma and pi stuff. Sigma bonds are, we're going to use a bunch of alliteration. Sigma bonds are single bonds. And again, it's kind of like a little O with a hat. Sigma is a molecular orbital or a bond, and it involves single bonding. We always have anything that's bonded together, whether it has a single bond, a double bond, or a triple bond, always has 1 sigma bond. So S for sigma. And with hydrogen, it's the S atomic orbitals that overlap. Sigma, single, S orbitals. Okay. And so those S orbitals in hydrogen overlap to produce that single bond, that single covalent bond. Notice the spherical shape becomes this kind of blob ellipsoid shape. Okay, that's the molecular orbital, that's the atomic orbitals in 2 atoms. In a single bond, it's the single bond that exists where the 2 electrons are just zipping back and forth between the two nuclei. Why would they hang out between the two nuclei? What charges a proton? P for positive. Electrons are negative, so they're going to be attracted to the nuclei. The electrons are going to live in this region in the center most of the time because each of the nuclei is going to be tugging on the electrons back and forth. Okay? When those clouds overlap and it gets to just the right point between the two nuclei, we have a single bond. Now, a sigma bond can also happen when p orbitals overlap. So fluorine. What family is fluorine in? Jack Conte. That's in the P block. What family is fluorine in? Caius. Fluorine, chlorine, bromine, iodine. What's their family? Go, Bethany. Yeah. Halogens. Okay, so they all end with 1, 2, S2, P, 1, 2, 3, 4, 5. So whatever halogen you are, you have S2, P, X, P, Y, P, Z, P5, right? You have 7 valence electrons, just need 1 stinking more electron. What does that mean in terms of the atom? I don't know which one's the P, X, P, Y, P, Z, it doesn't really matter, but these are representing, this is representing the p orbital. And so these two blobs together, these two clouds around the nucleus together is a single orbital. They could hold 2 electrons. With fluorine and chlorine and bromine and iodine, 2 of them have 2 electrons, 1 of them only has 1. Guess what's going to happen? And guess why all the halogens are diatomic? That half-filled p orbital wants a buddy, okay? And so the other half-filled p orbital in another atom is going to find it, and they're going to make a molecule. Notice that the shape of the molecular orbital, I think it should be larger, but in the middle, but they just made it kind of small in our textbook, so I just go with it. The space in between the 2 nuclei, again, is the bigger space. The ends are a little bit smaller. Because why? Because the electrons are going to hang out between the nuclei most of the time. So that's another way to get a sigma bond is 2 orbitals. And then maybe you can imagine this, maybe you can't, but it can also happen between an s orbital of one atom and a p orbital of another. So that's another way to have a single bond. And an example of that is, oops, I went too far, sorry about that. An example of that would be hydrochloric acid. Hydrogen only has an s orbital. Chlorine has the p orbital that needs a buddy. Hydrogen needs its buddy, and so they'll end up making a sigma bond, a single bond to make that compound. All right. Okay. That's weird stuff, I know. Okay. All right, the next one gets even weirder. So pi bonds are what happen when you have a double or a triple bond. Always start with a single, always start with a sigma to begin with between the 2 nuclei. And then the way we phrase it is kind of wonky because there's not a top or a bottom or a front or a back to a molecule. That's just not true. But when you draw it on paper, it makes some sense. Okay, so we say that pi bond is what happens. And this is cool because P for pi and P atomic orbital. So with a pi bond, you're going to have, this is for your doubles or your triples. And it's always going to be P atomic orbitals overlapping. Sometimes it's 1, sometimes it's 2. And I shouldn't say always because it's also, there's hybrid ones. But pi bonds are what's going to happen with a double or a triple. So how does that happen? Two p orbitals, separate atoms, come close to each other, and we get this weird blobby thing above and below that axis that goes between the nuclei. There's always a single bond in there already. Okay, the sigma bond is already formed before that double bond happens. And then the double bonds, the pi bonds are always weaker than the sigma bonds. So we talked about bond dissociation energy of single, double, triple bonds and how they vary depending on what the substance is. Just a pi bond is always weaker than a sigma bond because it's outside of the influence of the nucleus. I mean, it's still in the influence of the nucleus, but it's not directly in line with it. Okay. All right, so a single bond. So on your note sheet, I have it going across the top of the page, but I list them out vertically on the slide. So a single bond is one sigma, a double bond is a sigma and a pi, and a triple bond is a sigma and two pi bonds. One sigma, two pi bonds makes a triple bond. Now, just when you think you're kind of sort of getting the hang of this stuff, then I'm going to throw you another little curveball, and that's hybridization. And hopefully, so we're going to, oh, do you need to stop? Okay. Yeah. Yeah, you can. Yeah, got the passage right there. It's all right. So in biology, you should have talked about dominant and recessive genes. Talk about hybridization at all? Some of you yes, some of you no. So there's a term in animal science and in agriculture in general called hybrid vigor. And so how many of you have a purebred dog? Okay, what breed? German Shepherd. Oh, good. A Frenchie. Oh, perfect. Okay, so German Shepherds, to get registered, have to have an X-ray as a pup to get checked for, good idea, hip dysplasia. Anybody heard of that before? So they have problems with their hips, their pelvises, because of all the inbreeding. They have difficulty, they have arthritis, they have a lot of health problems. Frenchies, of course, have problems breathing and allergies and all sorts of things. We had a friend who had a Frenchie, had trouble with his wheelie, and so there's all sorts of problems. Okay, so this was a male, but he had to have surgery to get rerouted. It was really, really sad. So why do purebred animals have problems? They're cute, they look alike. Why do they have flaws? How do you get them to look alike? Inbreeding, yeah. So this is why you can't marry your brother or sister, okay? Not that you want to anyway, because they're idiots, but no. My brother, okay. But it's just, you are more likely to have those recessive traits, right? So if you take a purebred and another purebred and you do your cross, everybody's going to come out 100% heterozygous, right? But if you cross 100% here, what's going to happen? You're going to have 25 of these, 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 really the same, right? So 75% of the time, they're going to express the dominant trait. Part of the time, they're going to express the recessive traits. The more inbreeding you do, the more likely that recessive traits come out. Sometimes that's desirable. A lot of times it's deleterious. It's really bad. Okay, so whether you're a corn plant or a German Shepherd or a Frenchie, inbreeding to get that desired appearance will cause problems. So how do you fix that? You cross very different things. So mutts in general, not always, okay, are supposed to have less health problems because they're usually two very distant strains, but it's not always the case. Right? So also all the like corn that you buy, if you go driving down into the valley this spring and summer, be on the lookout. They'll have signs up that tell you what type of hybrid corn is planted in that field, because corn seed makers make a lot of money crossbreeding them in just the right way. Okay, so hybrids also happen with cars, right? A Prius is a hybrid car. Why is it hybrid? It has gas, it has a combustion engine, and an electric motor. Okay, it's both, right? So hybrids have both. Okay, so just trying to key you up here to where we're going with this hybrid orbital thing. It's kind of weird. All right, so in hybridization, when we're talking about chemistry, you get several different atomic orbitals, P's and S's, okay, that are combined and they make not spherical, not dumbbell, something in between. Okay? And that's a hybrid molecular orbital. It happens when they make molecules. So in the atom, nice straight sphere, dumbbell. We're not worried about the daisies and the freaky flowers, okay? But when they make bonds happen, something has to occur to spread out the electrons. All right. One in particular that's hugely important is carbon. So everybody should be able to do the electron configuration of carbon. Go. Take a minute and see if you can remember how to do that. Think about what line is carbon on, what block is it in, what column, how many electrons, valence electrons does carbon have? Somebody. Colin, tell me about carbon. What do you know? You can talk to your neighbors. You need more time? It does have 4 valence electrons. So what's its electron configuration? Like hydrogen's 1s1, helium's 1s2. Huh? Okay. How do we do that? Remember what line is carbon on? Whoop. 1, 2. Second line, right? What block is it in? P. What column of the P block? 2. So carbon ends with 2, P, 2. Not squared means there's 1, 2 electrons in it. Okay? Once that's done, then I know that the 2s has to be filled and the 1s has to be filled. 2 and 2 and 2 makes, which is carbon's element number because it has 6 protons. The neutral atom also has 6 electrons. Coming back like a bad dream. Everybody good with that? So normally what we would do, dx dy dz, 2, and there'd be 2 singletons, right? These are the only 2 electrons that need a buddy. This one has a buddy. This one has a buddy. They're all full. How does carbon always bond 4 times? What? How does it do that? What's going on? Think about what we were just talking about. These S's and the P's hybridize. So there's S, there's P, there's P, there's P. If one of these S orbital electrons is here, now we've got 1, 2, 3, 4. Spherical, a dumbbell, a dumbbell, a dumbbell, except they don't look like that. They look like something different. They look like the blobs on your paper. Did I put this one on there? Ooh, I didn't. Did I not put that on? I didn't. Bad teacher. So it's not spherical. It's not dumbbell. Okay, it's something in between. There's 4 sp3 hybridized orbitals that occur in order for carbon to bond 4 times. Okay, one of the s orbitals, kind of just the s electrons kind of smushes over. And that hybridization is what allows carbon to make 4 bonds, whether it's to all the hydrogens, like this methane molecule, or double bonds to carbons. It just depends. However, it always makes, if it's all single bonds, sigma bonds, it will make what's called a tetrahedral shape, excuse me, 109.5 degrees. Why is this important? It's because when we talk about molecular shapes, we also get a clue as to how the molecule is going to behave physically, melting points and boiling point trends. So in comes some hydrogens. Those hydrogens will bond to that sp3 orbital 4 times. And that makes our methane molecule. Okay. Play this little clip for you. And hopefully this makes sense. As you're watching it, it'll probably look like balloon creatures. Here we go.
Hybrid orbitals are formed by a mixing of the hydrogen-like s, p, and d orbitals that characterize a free atom. The 3 p orbitals are directed along the x, y, and z axes. When we mix an s and a px orbital, we produce 2 hybrid orbitals called sp, pointed in opposite directions along the x-axis. Mixing of an s with the px and py orbitals produces 3 equivalent hybrid orbitals in the xy plane. We call these sp2 hybrid orbitals. Notice that the hybrid orbitals have major lobes, which contain most of the electron density in the orbital. These are used in bonding to other atoms. Mixing of the s with all 3 p orbitals results in formation of 4 equivalent sp3 hybrid orbitals, directed toward the apices of a tetrahedron.
Have you guys ever been up to the mattress place up 108 on the right-hand side? So, I don't know if Sonora Mattress Works or something like that. The guy that owns that is an amazing balloon artist. He makes balloons. I should get him to make me a bunch of these. I can't do balloons very well, but the p orbital, remember, is these two lobes of a peanut. When you put in that spherical as well, it changes the shape, so you end up with one big one and then these little tinier ones that are all tied together in the middle at the nucleus, if you will.
Let's apply the concept of hybridization to ammonia. Here is the Lewis structure for ammonia. There are 4 electron pairs in the nitrogen valence orbitals. We know that an ammonia molecule has a pyramidal shape. The shape can be explained by assuming that the central nitrogen atom employs sp3 hybrid orbitals. The unshared electron pair occupies the 4th sp3 hybrid orbital.
So she said pyramidal. I usually say pyramidal. So remember I talked to you about ammonia, the 3 hydrogens, right, down at the bottom, and then the nitrogen up at the top. And then there's a lone pair of electrons. On some drawings, you'll see it kind of looks like rabbit ears. It's very similar to the tetrahedron of a carbon molecule, methane molecule, but that lone pair pushes them a little bit to 107 degrees instead of 109.5, which is what we're going to talk about on Thursday. So the shape changes because of the lone pair, and that makes the ammonia stickier to itself than methane. Methane is always a gas, but ammonia can be liquefied. Okay, and it's not the ammonia in your cleaning solution. Just 2 more slides and then we'll call it a day. Right. So in this one, we talk about what happens when you've got carbons, 2 carbons coming together to make a double bond. So the first thing that's going to happen is here on these green lobes, those are the sp2 now, because one of those sp3s is now just a plain old p orbital. The hydrogens come in, the hydrogens bond to the sp2, the carbons bond to each other with a single bond, and then a pi bond forms to form the double bond. So when you're looking at something like this, you've got 1, 2, 3, 4 hydrogens, the carbons are connected. All of those are sigma single bonds, so there's 5. And then to get that double bond, it has to kind of be outside of the realm of the axis, so we get a pi bond as well. And then the last one is just ethine. This is a common molecule as well. This is what most people call acetylene. So it's 2 carbons, 2 hydrogens, and a double bond and a triple bond. A single bond for the carbons, then a double bond, then a triple bond, and I lost my others. Oh, there it is. And I spent a lot of time bending over at this point in the year, which is good. I need to exercise, but that's how a triple bond forms. So again, a single sigma bond, always between the hydrogen. Hydrogen can't do anything but a sigma bond. And then between the carbon, at least 1 sigma, and then this time there's a double and triple, so 2 pi bonds. All right, I know this is weird stuff, but I promise you it will behoove you to invest a little bit. If you have to take college chemistry, this will come up again, I promise, and I will come up with some ways for you to study. Any questions right now? All right, yes. Yes, they go really fast. Yeah, the stuff we do in a year, they'll do in the first month. Maybe 2 months. I don't know. Depends. If you're at the UC, the first quarter is about the same as class. Yeah. Yes, and a lot more math and a lot faster. And there's a lot of other stuff that we're never going to get to.